Hello students, welcome back to the next lecture, which is lecture number 22, and we have been in the discussion on the two-body problem, and which means that the two-body problem is under the influence of the central potential. That was the discussion in the last class, and we have this particular conclusion. I am giving you the summary right now. So this is what is there in the last class. We started with the two-body problem where the two masses m1 and m2 are connected by the vectors r1, r2, and then the distance between the two masses were taken to be script r. So the diagram was there in the last class. So all these things are known to you, and therefore I am now writing down the summary. So this is the summary sheet, which will be helpful to recognize and remember what happened in the last two classes. And then the capital R is going to represent the center of mass of the two-body system. And you'll have to keep the diagram with you when I'm explaining. Otherwise, reading this expression and equation is not meaningful. So you will be having the class notes with you with the corresponding diagram, and then that will give you the refreshment. And our conclusion was that if you are going to use the R1 and R2 as the position vectors for the two-body problem, then ultimately we will be having 6 degrees of freedom. So that was the initial condition. Initially we started with the problem, and then we asked the question, what happens if you are planning to move to the center of mass coordinate system? So based on that, we have made a situation where we have shifted the coordinate. Shifting means translation. The translation of the coordinate, we translated to a place which is exactly nothing but the position of the mass m1. When you are moving that, the distance r1 becomes 0, and therefore r2 becomes the script r. How this has become script r, all the details are there in the last class once again. So if you have not seen, then you go back and see and then come back. Okay, keeping this equation, there is no point unless you know what happened in the last class. So then correspondingly what happens is, because the r1 vector has gone to 0, you will have to simplify this particular center of mass, and then put this 0 here. So when you put the 0 here, this term goes to 0, and what is left out is only this term. So you get m2 divided by m1 plus m2, and that's what is written here, m2 divided by m1 plus m2 into, you have an r2 here, but r2 has become script r. That's what we have this. So our conclusion is that the original equation that was there like this has been simplified it to the set of equations labeled 1. So we will say that this is your first equation. And then what happens is that we have also written down the corresponding Lagrangian in terms of the center of mass and the distance between the two masses. And this is the end of the last class. The end of the last class, we have the equation number 2. So we are now going to continue here. Okay, we are now going to continue at this particular point. So in this 3 minutes, I have given you the refreshment of what happened in the last class or last two classes. So our conclusion is that we had this equation number 2 where we have 3 degrees of freedom. Where from 3 degrees of freedom is coming is the set of 3 numbers to denote the script r. Okay, so you can ask the question, what happened to capital R? Capital R and the small script R, they are related to each other. So you don't require 3 plus 3. They are related. How they are related is that is there here. This is capital R and the script R are equal. Equal means equated. If you know one of them, suppose if I know the script R, I can calculate capital R. Or suppose that if I know capital R, you can calculate script R. Therefore, you don't require 3 plus 3, but instead you need only 3 of them. And the conclusion in the last class, at the end of the last class, was that it is sufficient to have 3 degrees of freedom for a two-body problem. That is the conclusion that we had. And we were in the process of further discussion. Okay, there is a place where he stopped, and we are now going to discuss on this, and then see what happens to the number of degrees of freedom if you are going to talk about the central potential in particular. So we have not at all discussed the speciality of the central force problem, because our main topic is the central force problem. The reason why it is important also we have discussed in the last class, and the primary reason is that the central force problem is some kind of a very special case of the rest of the problems, in that the Kepler problem happens to be a super integrable system. So this is the reason, one of the reasons why we pay so much importance and attention to the study of the central force problem. Okay, Kepler's problem is a very special example in that it is a super integrable Hamiltonian system. So the speciality is coming from the V of R, that's what is there here, and let us therefore further discuss what is the situation. Okay, so now let me explain the scenario. So corresponding to the equation number 2, in fact this particular diagram is also there in the last class, and now let us just refresh your memory that this is the mass m1, the blue color larger circle represents the mass m1, and then the coordinate is now brought here. That means the coordinate is exactly kept on top of the m1, and then the second mass is assumed to be a smaller mass, and it is far away somewhere. And then the distance between the two masses is the script r. So that is what I have written here. The origin of the coordinate system is also the mass m1. Okay, so this is how we have fixed the coordinate system, in which case what happens is there is a special thing happening here. What is special thing is the origin of the coordinate system is going to be equal to or approximately equal to the center of mass of m1 and m2. So this point is very important, and you will have to recognize or at least realize this is true. Okay, otherwise what happens is you think that the center of mass is somewhere else. So do you remember in the last class we have kept a dot here? So let me put a dot here. So we have kept a dot here and said that that was the center of mass. That was, so I am writing was here because that was the old configuration. That's why I am writing was. Okay, that particular point was the center of mass earlier. But now what is the latest center of mass is that this is the latest center of mass, which is exactly the origin of the coordinate system. So the center of mass has moved here in this direction and it has come here. How it has come here, that is what is the very important. You have to realize that how this center of mass has moved here. So only then you can recognize further on the Kepler's problem. And for understanding this particular detail, you'll have to realize with some numbers. So let me therefore explain that in the case of the two-body problem, what are we going to consider? So if you have some numbers, it will be interesting for you. So let us consider the first mass to be the mass of the sun. So I have written here, because we are saying that one large mass and one small mass, and the Kepler problem is essentially you can consider the what you call the orbiting of the planets around the sun. So therefore, let us consider the large mass to be m1, which is the mass of the sun. So let us take numerical value. Okay, 2 is okay. I am writing for easy remembering. You are supposed to write something like 1.97 into 10 to the 30, like that. So don't worry about that these fractions here. Similarly, the mass of the earth is something like 5.97. So that's fine. We will write down at 6 into 10 to the 24 kilogram. So these are the practical numbers. So if you have numbers under C, then you will be able to recognize and realize what is actually happening in the Kepler's problem and how things get slightly modified. And then you can easily understand why this system, or that means the Kepler's problem two-body system, happens to be a special case which leads to the super integrable Hamiltonian system. So in order to recognize and realize the situation, we need some numbers to get a feeling. So once you have these two numbers m1 and m2, you simply take a calculator and then divide m2 divided by m1. If you divide this, I have a 6 by 2, which is 3 here, and these two numbers, if you divide 10 to the power of minus 6. Which means forget about 3. 3 is a small number, so you can ignore this 3 and put a 1 here, not a problem. So which means that 10 to the power minus 6 times, okay, at least 1 million times smaller. Which is 1 million times smaller is the Earth is 1 million times smaller, means in terms of mass, I mean lightweight. Okay, we are not talking about the radius, it is the mass. So now since you are making a division, I have written explicitly no units for m2 by m1. Now this scenario you'll have to write down theoretically. Okay, these are numbers, fine. Theoretically, how do you write the scenario is that m2 by m1 is going to be much smaller than 1. Much smaller than 1 means you have a number 1 on your left hand side, you have a number 10 to the power minus 6 on the right hand side. You have two numbers with you and you ask the question who is very small and who is very big. Okay, it is like having $1 on one side. I have $1 on one side, and 10 to the power of $6. 10 to the power of $6 means $1,000,000. So $1,000,000 in one side and $1 in one side. You are keeping and then making a comparison, and then by making a comparison, essentially what I want to finally is, can I neglect something? That is what I mean to say. So why do you want to compare this? Is that I am making a comparison. Since you are going to put it in this side, let me write down here 10 to the power $6 on this side. We say that this is much smaller than that. What is the purpose of writing the much smaller than is that I would like to neglect something. I mean, which one would you want to neglect? Do you want to neglect $1 or 10 power $6? So it's very clear that you want to neglect. Neglecting means what? I have 10 to the power $6 with me, and you are having $1, and now you are saying that you will be giving that $1 to me. So after you give me the $1, what is the total money that I have? Means the conclusion that I am trying to say is that whether you give that $1 to me or not, it doesn't matter. That's what ultimately we are trying to write down in this equation. Okay, so in theoretically we write this kind of a scenario as m2 by m1 is much smaller than 1. And in this situation, when you add the two masses, okay, so you can easily understand the dollar addition here. And now that's what exactly now we have written down, that the mass of the sun plus the mass of the earth we are going to add. How are you going to add a number like this? Okay, so interestingly, you can add like this. So this is a 2 here, so write down the 2, and then this is 10 to the power 24, and this is 10 to the power of 30. So there are 6 orders of magnitudes are smaller. So put 6 zeros here. 1, 2, 3, okay, 4, 5. 1, 2, 3, 4, 5, and that will be 6. And then now you can put a 6 here. So this particular 2 has come here, and this 6 has come here, and the difference, the 6 zeros are now added here. And ultimately then we will be having into, you have 10 to the power of 30. So this is how you perform the addition finally. So m1 plus m2. And so what is the conclusion? That after doing the addition, what happened is that 6, that means the mass of the earth is giving a small addition at the end here, which means that I am getting back the original mass of the sun itself, right? So therefore, whether you add the mass of the earth or you don't add, it doesn't matter. That is what it means to say. And this is very important. This is the scenario that we are going to use in the simplification. So once you understand this, now we are asking the question, when one of the masses is so big, okay, when one of the masses is so big, which means that the ratio is going to be so small, we ask the question, because of this reason, what happens to the equation number 2? Because equation number 2 is the place where we stopped in the last class. So we will have to now simplify that particular equation under the condition that m2 by m1 is very small. Okay, so you understand what is that we are trying to do in today's work, that we are going to consider the scenario of a very large mass and a very small mass combination for a two-body problem, and our conclusion is this. So let me put an arrow here. You understand that the first conclusion that we can do is that m1 plus m2 will be approximately equal to m1 itself. So this is the conclusion number 1. How you got m1 just now? I have shown you here, and this one. So this is there, right? This is the example. m1 plus m2 will come back to m1 itself. m1 is, what is m1? This number, 2 into 10 to the power of 30. So it is the same number will come back to you, and therefore the first addition, this is the first expression that we have. Why do you want this particular equation? Is we have an m1 plus m2 in this equation. See here, we have m1 plus m2 in this equation. That is why we are going to simplify. So first point is over. Okay, what about the second one? The second one, we have m1 m2 divided by m1 plus m2. So that expression we will have to evaluate. So therefore we will try to simplify what happens to the condition for the m1 m2 divided by m1 plus m2. So what will happen to this expression? So let us evaluate that. Okay, so we will write down this particular expression like this. Let us take m1 common, which means that m1 into m2. m1 I am taking common in the numerator. In the denominator also I will take m1 common. So if I take common, I will get 1 plus I get an m2 by m1. So that's all. So this is what happens. Then you will cancel this expression and then write down m2 divided by, we get a 1 plus, so this is your m2 by m1. This is where you are going to apply the rule. m2 by m1, what is there? m2 by m1 is much less than 1. So I'll write down 1 plus a quantity which is going to be much less than 1. That's what I'm going to add. So what kind of number is this? If you ask the question, what kind of number is this? It is something like 10 to the power of minus 6. Now that is what I have now explained to get a feeling what kind of number it is. See, here it is there. This is the number. m2 by m1 is approximately equal to 10 to the power of minus 6. So you are going to add 10 to the power of minus 6 to 1. That means essentially we are going to ask the question, what is 1 plus 10 to the power of minus 6? How much is this? We say that after adding, we will get 1 only. Because 10 to the power minus 6, whether you add it or not, there is a small fraction at the 6th digit. That's okay. But that's not going to affect your entire calculation. For that reason, what we'll do is, rather than saying equality here, we have written equality here, we will say that it is approximately equal. And the approximation is good approximation. Okay, there is nothing to worry about, losing the 6th digit at this particular point. And that is what we try to say, and therefore ultimately what happens? So 1 plus nothing, so much less than 1 means nothing, so 1 plus nothing, so ultimately I'll be getting an m2 here. So I'll say that the similar approximation, I'll write down that m1 m2 divided by m1 plus m2. So this expression goes to m2 itself. So this is the condition B. So we have A here, so this is the A you have, and this is the B you have. So now you can put these expressions for A and B in our original equation. So what was your original equation? That is the Lagrangian equation, you remember? That is the equation number 2. Okay, so let us substitute in equation number 2 and then write down the expression. So let me write down that. So here we can write down like this. So now I will write down that I need some space, so put line here. So now here I will write down. So let us substitute. Okay, so let us substitute the condition number A, or the simplified expressions A and B, in equation number 2. So if you are going to do this substitution, what are we going to get is that the Lagrangian is going to be half into m1 plus m2 was the first expression, so that will become m1. Then you will be getting capital R vector dot square. Then you have a plus, then you have a half. Then you have this expression m1 m2 by m1 plus m2 you are going to have, which is now going to be approximated to m2 itself. So I'll write down this m2, then multiply by the script R vector dot square. That is the only simplification, minus nothing happens to the potential and simply keep it. So nothing happens to original potential V of R. From the day one we are keeping the same V of R. So that is nothing is going to happen because of the coordinate transformation. And this is the simplified expression corresponding to this equation number 2. So now we have greatly simplified in the sense that when compared to the yesterday's equation, today's equation looks fairly simple. So this is the first point that you'll have to note down. The second important point is, and not only this, there is something interesting and very important is, and in addition what is going to happen is, what happens to and what happens to the center of mass. Center of mass equation is actually how much? So in center of mass equation is original equation is m1r1 plus m2r2. This was the original equation divided by m1 plus m2. Then after that what happened? After that what happened is we have shifted the coordinate. Okay, we have moved the coordinate, translation of the coordinate, and therefore this fellow, the first r1 became 0. Then we are left out with only m2. So we have an m2 divided by, this is m1 plus m2. Then this r2 has become a script R vector. Okay, so that is what happened actually for the R vector. There is nothing new. If you want, I'll show that it was there already. If you are writing in the note, it will be already there. It is there. So actually I am talking about equation 1. This is the one. So in the summary that I told in the very beginning, so that equation you keep it now. And then we are now discussing what is happening to the center of mass. So this center of mass is what you are going to simplify. So let us write down that this is m2, into the script r vector divided by, once again you take m1 common here, we will be getting 1 plus m2 divided by m1. And then apply the condition. What is the condition? You know, the ratio m2 by m1 is very small, and therefore we will be having m2 into the script r divided by m1 into 1 plus a quantity that is very small. Okay, so that's what you have, and that's all. So you are now making a conclusion. The conclusion is that we will be having m2 into the script r divided by m1. So this will be the expression for the r vector. Okay, so whenever we need, we can always make this kind of simplification, and then ultimately we have once again this kind of a scenario. But now comes much more interesting. See, here there are two, we are now once again we have to apply. See, 1 plus nothing, so that is becoming 1. So ultimately we have m2 by 1, that is we have written. But again you see m2 by m1. After simplifying, now we are seeing m2 by m1 once again. So therefore, now this is interesting. This m2 by m1 that is there here, that whatever that was there here in this scenario is going to be a very small number. So let me write down that it's going to be much smaller than 1. Then that is getting multiplied by, so I'll put multiplied by script r vector. So this is the place where you have to be very careful in understanding what is the meaning of this equation. So that's what you'll have to realize. Once you understand this, then the rest of the thing is very easy. See, there is a very small number. Very small number means take something like 10 to the power of minus 6. That is what is the number that you have, m2 by m1, practical number I'm talking about. And then you take the distance between the two masses. Okay, and if you are going to take the distance between the two masses, then you'll have to take some practical number and then substitute. So okay, so now we are trying to evaluate. So please understand what we are trying to do. In order to get the feeling, you need numbers. So the center of mass is given by a small number. Small number means of the order of 10 to the power of minus 6 in our problem, because in Kepler problem, small number in this in our cases is the ratio of the two masses, that is 10 to the minus 6, multiplied by the script r, and the script r is the distance between the sun and the planet. And in particular, if you are going to consider the earth as a scenario, as a typical example, then r is happening to be 148 million kilometer. Okay, so I'm going to substitute that kind of a number, 148 million, then we have a kilometer here. So that is the typical value for the script r. Anyway, vector is not required. It's a distance between them. We are multiplying, and we would like to know how big and how small it is. That's what is the interest now. So in that way, the direction we are not interested. So what kind of number will come if you multiply? That then only I can write down here, right? So what is the value that I should write? So ultimately what happens is that the number is approximately 148 kilometer. So that is the kind of number, especially if you are going to take the sun and the earth system. So now the question that we are interested to write down is that how do I write 148 kilometer in terms of the capital R or in terms of the small r? That is what I mean to say. Okay, so to write that, in order you'll have to appreciate what kind of statement that we'll have to write down here. In order to make what kind of number to write, you will have to realize and get a feel for what is this 148 kilometer. Is it a small number or it's a big number? With what number do you want to compare and make a conclusion? So that should be clear. Otherwise, you don't know what to do with the 148 kilometer, right? So for that purpose, what you do is, where to compare this 148 is, you'll have to compare with the radius of the sun. Why do you want to compare with the radius of the sun? Why should you compare? That question comes. The answer will come. Capital R represent the center of mass of the system, which means that if this is the sun, for example, and if this is the earth, for example, and from the center of the sun, you're going to draw a line like that. Okay, that is representing the R. So this distance is what is written as, this distance is exactly 148 million kilometer. Okay, that is clear. Now what is this 148 kilometer is that from this center you will have to move in this direction by a distance of 148 kilometer. That's what is the meaning. Okay, and once you understand this, then you will be able to realize what is that you want to do. Now, to get the realization or to get the feeling, first thing you should know is how big is the sun. Okay, then only you know 148 kilometer is what. Okay, so for that reason, I will now write down that the radius of the sun, that is from here to here, from here to the here, whatever this particular distance is typically the radius of the sun, right? So that number, let me write down here, the radius of the sun is, okay, kilometer, not kilogram. Okay, so that's the number. So of course these numbers you can always refer and verify, okay, from the data. It is 7 into 10 to the power of 5 kilometer is this distance. This is the distance, okay, from here to here, 7 into 10 to the power of 5. Okay, now what is this 148 kilometer is that you'll have to move and then walk like this 148 kilometers. So how big you will be 148 kilometer in front of 7 into 10 power 5 kilometer. Okay, so you have 7 into 10 to the power 5, 1, 2, 3, 4, 5, then you have 148 kilometer. So you'll have to compare these two numbers, and you're trying to say that you move away and then you walk and then keep this particular place. So now you see the vertical line that I am keeping is the place where you have moved and then standing at 148 kilometer. That's what is the meaning. So we say that this number which you are going to write down is going to be once again very, very small in comparison to the expression. So let me therefore write down that for practical purposes this is 0. This is the point that you'll have to realize. Okay, what do you mean by 100? 0, why do you are putting? You can put 148. Yeah, 148 we can put, but you see when you are performing theoretical calculation, we have to perform comparison of the numbers, ratio, and then how big it is or how much it is moving approximately, etc. 148 keeping here there's no meaning because it's not an absolute number we are going to use. So at least you should be now in a position to appreciate, or you must be in a position to agree that okay, 0 is agreeable. If that is not agreeable, then you are not understanding or you are unable to feel what is that we are trying to do. So the meaning of r equal to 0, what do you mean by this is that the center of mass of the two body system is lying at the center of the sun itself. That is the meaning. So let me write down the meaning, then let us see whether you are convinced with the statement. The center of mass of the sun-earth system lies at the center of the sun itself. The meaning of the 0 is that 0 means that is the center of the sun. So you don't have to move 148 kilometers. So 148 kilometers is too small. Whether you move it or not, it doesn't matter. You better stay in the center itself. That is what it means to say. Ultimately, that is the meaning. The statement clearly tells you that center of mass of the two bodies system lies at the center of the heaviest object. In this scenario, sun is the heaviest object. So this is the meaning of this particular expression. R is approximately equal to 0. So this is very important situation. And therefore what happens is, and this is first point. Okay, let me also write down the second point, then we can make a conclusion now. The second point is in addition to this. Okay, so let us cancel this. And in addition, this is also another point. In addition to this, the coordinate system, where did you fix the coordinate system is? The coordinate system is fixed. Where did you fix? You fixed at the point r equal to 0. Which, see, first of all, r is approximately equal to 0. So for practical purposes, it's okay whether you approximate or whether you say equal. The numerical numbers will be fluctuating and some 10th digit or 8th digit. Okay, that's all about it. That's the meaning of the approximation. And therefore, you can always say that r is equal to 0 is the meaningful expression. And our conclusion is that at this particular r equal to 0, you have fixed the coordinate system, right? That is what we have been discussing. So this is the coordinates if you are going to have. This is how you started the problem. You put the coordinates here. So this is first point that you have. In addition to this, the second point is we refresh our memory that the coordinate system is fixed at r equal to 0. And therefore what happens is, what will happen is, in case if the sun itself is going to move, okay, whether it is moving or not, that's a different story. In case if it is going to move, then we ask the question, what will happen to the r dot? You ask the question, what will happen to the r dot? So this you have to think and tell. Okay, don't use mathematics. If you are talking about mathematics, then you are going to make a mistake. Okay, so let me here give you some example. You please understand this. If the position vector r is equal to 0, this is position vector. Please understand. If the position vector is 0, then the velocity vector at the same time, okay, at the same time, I will write down at the same time. Time is I am not writing. R of t, I mean to say, okay, is not equal to 0. Not necessarily. So this is the point that you have to be careful. Mathematically, what happens is, typically in calculus, what they will teach, they will say that whenever some y equal to 0, and if you differentiate y is 0 means dy by dx should be 0, right? So if the original quantity is 0, if you differentiate, that will be 0. So that will be there in your mind. So now you have to be careful that that concept will not work here. If the r is equal to 0, then dr by dt is not equal to 0 at the same time. So this is the concept that you have to be careful in the sense that r and r dot represent two different quantities. One is the position of the particle and another is the velocity of the particle. So therefore, keeping this in mind, now you have to tell that if r is equal to 0, can we say r dot equal to 0 means not because of calculus. Okay, if according to calculus it is not equal to 0, not necessary. Equal to 0 is a very special situation, but in general situation r dot is not necessarily 0 if r is 0. So that keeping that point, once again we will come back here. Now already we made a decision that r is equal to 0. Therefore, can we say anything about r dot? The answer is we cannot say anything, because this is the point to be noted. Therefore, we cannot say that r dot is 0. But that is a but here. But since the coordinate is fixed, here, where did you fix means it is fixed at r equal to 0, and therefore we can say r dot is 0. So this is a different story. Okay, it is like, you are traveling inside a car. If you are traveling inside the car and you ask the question, are you moving? Then you say, I am not moving. I am sitting in the driver's seat and I am wearing the seat belt. I am not at all moving. But the person outside will say that no, you are moving at 100 km/h. So that difference you are able to feel, right? So that difference is what I am trying to say. Once the coordinate system is fixed, then if the entire system is going to move, then the velocity for that person is not at all there. That is what we mean to say. So r dot means with reference to this system, in case if the sun is moving, remember this, in case if the sun is moving, then we will in our expressions write down that the velocity of the sun is equal to 0. The reason is the coordinate system is sitting in the sun. That is the reason. So reason should be very clear, not because calculus. Okay, calculus doesn't tell whether it is equal to 0 or not. Okay, because I am also sitting on the sun, and if the sun is moving, then I will say that I am not moving. Okay, because we are both together. So this concept is crucial. Why it is very crucial is we are going to substitute this r dot equal to 0 in our expression. So where is the expression for r dot? Now let us go back here, which is your original equation number 2, which we have simplified. Yeah, here it is. Equation number 2 was simplified, so let me write down this as equation number 3. Okay, equation 2 is what we started, and there is an r dot square is there, right? So there we are going to substitute 0. That is why I am explaining. Okay, so when you substitute 0, the first term completely goes out and we are left out with only one term, and here you have to be careful that this is m2. Okay, 1 and 2 is not important. At least you remember that it is a smaller of the two masses. When you have two masses, what is m2 means? It is the smaller of the two masses. That's all about it. Whether you use m2, m1, m3, that is not important. So out of the two body system, m2 represents the smaller mass. That's all about it. So let us therefore remember this point, and let us say that this particular term goes to 0. So I'll cut this now. So like this you can cut, for example, this particular term goes to 0, and let us therefore write down what is left out. Okay, whatever is left out, that expression we are going to write down. So let me therefore go down and then Let us write down that. And because of these reasons, so finally or ultimately what happens is that our equation 3 is now getting simplified, and we will write down that the Lagrangian of the two-body system, okay, Lagrangian of the two-body system, when the center of mass is coinciding with the larger mass, which is the sun, in that particular scenario, we have the simplified equation half into the smaller of the mass that you have multiplied by the distance of separation of the two masses, then square this, then minus the potential energy, nothing happens, so we'll write down this. And that's all. So this is the simplified one. Now it is very clear how this Lagrangian is looking like. First of all, how it looks like. So this is very clear that this looks like, half mv square. There is no doubt about that. This is half mv square. So certainly this is looking like kinetic energy of a single particle system. Do you agree for this? Only one particle is there. So only one particle with only one mass. Okay, M1 is not at all there. M1 is gone. Now no more. So only you have M2. Okay, so only a single mass is there. Therefore, this is a kinetic energy of a single particle, and you have some potential acting on. A potential energy can be acted on this particular single particle. That's all about it. So you have a potential energy and you have a single particle, and therefore, so remember, and therefore our conclusion is that this entire expression clearly tells you that this is the Lagrangian. Okay, this is the Lagrangian of a one body problem. Of course, it's a particle only, really, but rather than saying particle, since these are the planets, for example, in practical scenario, instead of saying one particle, we say it is one body. That's all about it. There is nothing else changes, as I already told you. Practically, this is a particle mechanics. So this is a one body problem. So what happened finally? We started with the two body problem, right? And 2 classes back. I think 2 lectures before, we started with the two body problem, and now we have a one body problem with number of degrees of freedom. Let me write down that for clarity. Number of degrees of freedom, still we have 3 only. Okay, we have 3 number of degrees of freedom. So our conclusion, what is your conclusion ultimately that I am trying to say is that a two body problem has come down to a one body problem with the number of degrees of freedom is equal to 3. And we are going to see what is because of the property. We have till now we have not discussed anything on the speciality of the gravitational potential. Okay, if we discuss that, then something is going to happen to the number of degrees of freedom. So that part we will see in the next class.